Welcome, wonderful chemistry students. This is Unit 6, Introducing Dimensional Analysis and the Mole. When we first introduce the mole in chemistry, a lot of students like to think about the rodent, the mole, something that has tiny ears, the pointed snout, a long, powerful tail, likes to dig in the ground. However, this is not the mole that we're talking about. We're talking about a number that is equivalent to other units of measurement, similar to 1 meter is equal to 1,000 millimeters, 1 gram is equal to 1,000 milligrams. So it's used as a conversion factor in chemistry since we have very small things like atoms and molecules that are not seen by the human eye. A lot of atoms and particles and molecules make up the regular stuff we talk about in chemistry. So before we introduce the mole and start doing some mole conversions, let's practice doing some basic dimensional analysis conversions just to make sure you understand what goes in the numerator, what goes in the denominator, why we put numbers in the numerator and the denominator, and just make sure we understand kind of how we set up a problem and why we do it the way we do it. So I asked this question, what do these have in common? So I have 1 dozen eggs over 12 eggs, 1 centimeter over 1 meter, 60 seconds over 1 minute, and 1 minute over 100 centimeters. So these are called conversion factors. These are all equal to each other. So 1 dozen egg is the same thing as 12 eggs. 100 centimeter is the same thing as 1 meter. They're all equivalent to each other. And when you have these things that are two numbers that are equivalent to each other, it doesn't really matter the units, okay? These are called conversion factors, and they allow us to convert from one unit to another unit. So the definition of a conversion factor is two equal quantities written as a fraction that equals 1. So we just saw a couple conversion factors on the previous slide. So we do a lot of dimensional analysis in chemistry. So it's multiplying measurements by conversion factor to change units. So you've done a lot of this in your basic algebra class. The measurements value doesn't change because it's being multiplied by 1, which again is your conversion factor. So again, we're going to practice doing some basic conversion factors with units that you are familiar with, like meters, centimeters, grams, liters, before we get into units pertaining to chemistry units, moles, particles, grams, things like that, that we will be doing within this unit. All right, so this problem is asking us to take 0.455 centimeters and convert it into meters. So this is the conversion factor that we're going to be using, and I always recommend to the students that they start off with whatever is given to you in the problem. So I'm given 0.455 centimeters, so I'm going to write that first. And I multiply it by my conversion factor. So I say whatever unit it is here, drag that down into the denominator. So I'm write that centimeters here. And then I write the other unit I'm solving for the other part of my conversion factor on top. So if you are unsure what number goes in the numerator, what goes in the denominator, just pay attention to your conversion factor. So I see centimeters here, and 100 is with that, so I'm going to write 100 in the denominator. And the other conversion factor is 1 meter, so I'm going to write 1 meter there. So centimeter divided by centimeter cancels out, and I'm just left with the unit that I'm asked to solve for. So it turns into 0.455 times 1, all of that divided by 100. So you plug that into your calculator, and you get 0.00455. So with any math related in chemistry, we would need to remember our sig figs. Going back to our problem, 0.455 has 3 sig figs. Forgot my units here. So I could leave it as is because this number only has 3 sig figs, or I could also convert this into scientific notation. So if I move this over 1, 2, 3 times to the right, it turns into 4.55 times 10 to the 1, 2, 3. I moved it 3 times to the right, and to the right is negative. So either or would be fine. Some people like to write it, they call it the railroad method, so it's the same thing. So you can just kind of write it like this, and whatever you're given to in the problem goes in the top left corner. Again, whatever unit is here gets dragged down here. And so I have 1 meter to 100 centimeters. So rather than writing out multiplication or division, you just draw these lines, and they call it the railroad method. And either way is fine. For this next problem, we were asked to convert 120 liters into milliliters. So here's our conversion factor. So this actually should be 1 times 10 to the 6th power. So starting out with what is given to me in the problem, 120.0 liters. This has 4 sig figs. So I'm going to need to make sure my answer has 4 sig figs. Either doing method by just writing out the multiplication or doing the railroad, either or is fine. This unit gets dragged down there, so I'm going to write liters down here. So I look here, I see 1 liter, and the other conversion factor goes on top, 1 times 10 to the 6th milliliter. So liter cancels out with liter, and I'm just left with the unit that I'm asked to solve for. Plug that into your calculator, and it comes out to be 120 million milliliters. But I cannot leave it like that because that only has 2 sig figs. So I need to convert this into scientific notation. So I have 4 sig figs in my answer. So if I pretend there's a decimal here at the end, use a different color. 1, 2, 3, 4, 5, 6, 7, 8. So 1.200 times 10 to the 8th liters. So our coefficient, 1.200, has 4 sig figs. And we can leave it as such. All right, for the next problem, we're asked to convert 0.045 kilograms into centigrams. So you could possibly Google one conversion factor to go from kilograms to centigrams, or you could possibly know that in 1 kilogram there's 1,000 grams, and in 1 gram there's 100 centigrams. So sometimes it might require you to do 2 conversion factors. So that's what we're going to do in this case. So always start with what's given to you in the problem, 0.045 kilograms. All right, I'll write it out the other way this time, times your first conversion factor. Whatever is here gets dragged down here, kilograms. So I look at my conversion factor, I see a kilogram right here, so I'm going to use this one first. So in 1 kilogram, there's 1,000 grams. Okay, and then I'm not yet to the unit they're asking me to solve for, so I'm going to multiply it by my next conversion factor. So I'll multiply it by, again, whatever unit is here gets dragged down here. So this kilograms gets canceled out with this kilograms, grams go down here. So got that. So now I got to do my other conversion factor, 100 centigrams. So now this grams cancel out with this gram. I'm only left with the unit that they're asking me to solve for. And I plug this into my calculator, so it's 0.045 kilograms times 1,000 times 100, and oops, I forgot to add in down here, this was 1, doesn't really matter, and all of that divided by 1. So everything in the numerator divided by whatever the denominator comes out to be. So we plug this into our calculator, and it comes out to be, 4,500 centigrams. And looking back into my problem, 0.045 has 2 significant digits, so my answer can only have 2 sig figs, and just the 4 and the 5 are significant, so I can leave it as such. or I can convert it into scientific notation. 4.5 times 10 to the 1 2/3 power centigrams. We did 2 sig figs. All right, for our last one, we are asked to convert 67 days into seconds. So you might want to think of what you know. So I know in one day, there are 24 hours. And in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. All right, so those are my conversion factors. So always start with what's given to you in the problem. 67 days. You do the railroad method this way. Okay, whatever unit is here gets dragged down here. So days. Okay, so I look over here, I see day here, nothing else in the conversion factor. So in one day, there are 24 hours. Okay, not yet to seconds, so I've got to multiply by another conversion factor. Whatever is here gets dragged down here, so I'm going to write hours down here. So I look here, in 1 hour, there's 60 minutes, so that's my next conversion factor. In 1 hour, 60 minutes. And then, still not to seconds, I know this unit goes written down below, my denominator. For my last conversion factor, in 1 minute, there are 60 seconds. So I go through, days cancel out with days, hours cancel out with hours, minutes cancel out with minute, and I'm only left with the unit that I'm asked to solve for. So I go through 67 times 24 times 60 times 60. Everything in this numerator gets divided by everything in this denominator. So we plug this into my calculator, and this only has 2 sig figs, so we need to make sure our answer only has 2 sig figs. All right, so my answer, my calculator, I plug all those numbers in, and I get 5,788,800. But again, I can only have 2 sig figs, so I need to round this. So if I pretend there's a decimal here, 1, 2, 3, 4, 5, 6. Okay, so it's going to be 5 point. This 8 can round that up to an 8. So 5.8 times 10 to the, what do we say, 1, 2, 3, 4, 5, 6. Sixth power, and that gets me 2 seconds. So go ahead and pause the video and try to work through these problems on your own, and then come back to check your answers with mine. All right, walking through these problems. The first one, we had 30.0 kilometers per hour, needing to convert to meters per second. So here we have 2 different types of units going on. We have units of measurement and units of time. So I've color-coded those. So kilometers to meters, I know my conversion factor is 1 kilometer is 1,000 meters. In hours to seconds, in 1 hour, you could do hours to minutes and minutes to seconds, or I knew in 1 hour there were 3,600 seconds. So it doesn't really matter if you convert kilometers to meters first or hours to seconds. Either way, you'd get the exact same answer. So I wrote first what was given to me in the problem. So I did 30.0 kilometers per hour. And I chose to do my units of distance first. So I used this conversion factor first. I know kilometers goes in my denominator, so they can cancel out. So 1 kilometer is the same thing as 1,000 meters. So now I've converted to the unit of measurement I'm asked to solve for. And then now I can do my second conversion factor. So hours is in my denominator. So I need it in my numerator. So I do 1 hour over 3,600 seconds. So now hours cancels out with hours, and I'm only left with meters over seconds. So I plug this into my calculator. So 30.0 times 1,000 times 1. All of that divided by 1 times 3,600. And I have 3 sig figs in my problem, so I needed to have 3 sig figs in my answer. For the next one, similar, I have units of mass and units of time. So I take 7.50 grams over seconds, and I'm going multiplying it by my conversion factors of mass. So in grams to grams, 1 grams is the same thing as 1,000 milligrams. And then seconds is in my denominator, so I need a seconds in my numerator so they can cancel out. So in 60 seconds, there's 1 minute. So 7.50 times 1,000 times 60, all of that divided by 1. And I come out with 450,000. I have 3 sig figs in my problem, so I need 3 sig figs in my answer. So I need to convert this into scientific notation. And it turns into 4.50 times 10 to the 5th milligrams per minute. In the next 2 problems, I'm giving you a clue down here. So if something is cubed or squared, just take the first power relationship and square or cube both sides. So in this first one, I know that in 1 meter, there's 100 centimeters. So if I just square both sides, I can get my new conversion factor, which turns into 1 meter squared is equal to 10,000 centimeters squared. So start with what's given to me in the problem, 150.0 centimeters squared. I look at my conversion factor, centimeters squared, it was 10,000, so that needs to go in my denominator. So centimeters squared divided by centimeters squared, they can cancel. I have 1 meter squared up top, 150 times 1 divided by 10,000, and I come out with 0.015. I need 3 sig figs in my answer because that's what was given to me in my problem. So I convert it into scientific notation to get 4 sig figs in my answer. And then my next one, I'm going from centimeters cubed to millimeters cubed. So I know in 1 centimeter, it's the same thing as 10 millimeters. So I just cube both sides, and it comes out to be 1 centimeters cubed is the same thing as 1,000 millimeters cubed. So start with what's given to me in the problem. Centimeters need to be divided by centimeters so they can cancel out. And then I put what I'm solving for in my numerator. 9.48 times 1,000 divided by 1, and I come out with 9,480. I can leave it as such because this number only has 3 sig figs. All right, here are a couple practice problems already solved out. If you wanted to go ahead and solve them out first on your own, if you need more practice, if you feel like you got a good handle on this, you don't need to worry about this, but here are the answers, and you can double check yours with mine. All right, so now that we have kind of a good grasp on dimensional analysis stuff and a refresher, we can now get into talking about some mole conversions. So like I mentioned before in the very beginning, a mole represents a number, and the specific number is 6.02 times 10 to the 23rd. If you took that decimal and you expanded it 23 times, it would turn into this nice long number. Really, really big. So it's much easier to write into scientific notation than it is to write in the expanded form. So just like the word dozen represents 12, a mole represents 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd what? So if you have 1 mole of any element, you have 6.02 times 10 to the 23rd atoms of that specific element. 1 mole of an element also means that you'll have that element's atomic mass in grams. So it just depends on what we're trying to solve for, what they're giving to us in the problem to really determine what the unit for 6.02 times 10 to the 23rd actually is. So going off the last slide, again, looking at the periodic table, if this is our element symbol for potassium, if I have 1 mole of potassium, I also know I have 6.02 times 10 to the 23rd atoms of potassium, which is the same thing as saying I have 39.10 grams of potassium. So you just got to look on the periodic table and find that, use that average atomic mass that's on the periodic table, and that will stand for the molar mass of that. Same thing with carbon. If I have 1 mole of carbon, I know I have 6.02 times 10 to the 23rd atoms of carbon, or I could say 1 mole of carbon is the same thing as 12.011 grams of carbon. We're going to use the exact mass that's given on the periodic table. We're not going to round up or round down. So we've also talked about other things like molecules and ionic compounds in the past. So if you have 1 mole of any molecular compound, we could say 1 mole is the same thing as 6.02 times 10 to the 23rd molecules of that. Or if we have an ionic compound, we could say 1 mole is equal to 6.02 times 10 to the 23rd formula units of that. So I'm kind of giving you a warning down here. It says, as a warning, many people or worksheets, if you look on Google or things like that, misspeak and say molecules when they mean formula units, or if they mean atoms. You just kind of have to deal with it. So an example using a ionic compound would be sodium chloride. So I could say 1 mole of sodium chloride is the same thing as 6.02 times 10 to the 23rd formula units. My 23s, the subscripts, didn't transfer over well when I copied this into this notation device. Or it's the same thing as saying 1 mole is the same thing as 58.44 grams of sodium chloride. And where I got this grams of sodium chloride is I looked on the periodic table. There was 1 atom of sodium, 1 atom of chlorine, so 22.99 plus 35.45 using the exact numbers on the periodic table. And so this 58.44 grams is the same thing as this and 1 mole. So just clearing up some terms, whether you're Googling information or reading about it in other textbooks and things like that. For the most part, I use the term molar mass, okay? Molar mass is what we get from the periodic table, just like we did on the previous slide. The units are grams per mole, right? The molar mass. Other units that you might see would be GAM, which stands for gram atomic mass, GMM, grams of molecular mass. For example, this would be if we were dealing with one singular element. This would be if we're dealing with a molecular compound or a molecule. Gram formula mass, that would be dealing if we're dealing with an ionic compound. If you want to be super specific, whether like we use GFM for ionic compounds and GMM for molecular compound, again, I just use the term molar mass and that encompasses all 3 of these. So there is a relationship between moles and volumes of gases, and again, it's specifically pertaining to gases, not liquids or solids. So gases have different molar masses, but all gases will occupy the same volume. 1 mole of any gas at standard temperature and standard pressure, and we'll talk more specifically about these when we get into gas laws. It's a fixed temperature and a fixed pressure. 1 mole of any gas will occupy 22.4 liters. And that's because if you increase or decrease the temperature, that's going to affect the amount of space, the volume that gas will take up, and the same thing with pressure. If you increase or decrease the pressure, it will adjust the volume, the amount of space that gas takes up. So this is another conversion factor that we will use, which we'll see again on a slide coming up, is that 1 mole of any gas, and again, you can know that it's a gas by looking at the abbreviation down below, like written as a subscript, is equal to 22.4 liters of that gas for any particular gas. Doesn't matter which gas it is. So this is a flow chart that is also in your digital notebook. So you can use it if you don't know what conversion factor you use. This right now we're going to be just going from moles to mass, or mass to moles, or moles to particles, particles to moles, or moles to volume, volume to moles. And I just want to say any gas that I'm going to be giving you in any worksheets or any assessments within this unit, they're always going to be a STP, because that's the only way we'll be able to use this conversion factor. None of the gases won't be a STP. So if I'm giving you moles and I'm asking you to convert it into how much space that gas will take up, you need to multiply by this conversion factor. Same thing, moles to particles. We are going to be using this conversion factor. And if you're going from moles to mass or mass to moles, we just need to add up the mass. Again, we get this from periodic table. We just use the masses that are on the periodic table to get those molar masses. So use this, learn it, love it. It'll help you when we get into our stoichiometry unit also. One last thing to mention is that down here on the right, this particle, this could be molecules, or this could be formula units, whether we're dealing with ionic compounds or molecular compounds or atoms. All right, let's practice some problems pertaining to mole conversions. So looking at here, it says, what is the mass of 1 mole of calcium sulfate? So I know that 1 mole of any substance is equal to the molar mass of that substance. All right, so I know I get this from the periodic table. So I look, and again, depending on what periodic table you are, they round to different number of digits past the decimal. So I'm just, again, if you have more digits past the decimal, it just makes your answer more precise. Just looking at the periodic table that I have in front of you, I know that calcium, I see it has 40.08. I'm going to add these masses together. Sulfur is 32.07 and oxygen is 16, and there's 4 of those because that's what that subscript 4 shows me. Multiply that by 4. So I multiply that, add them all up, and I get 136.15. So 1 mole of calcium sulfate is the same thing as 136.15 grams. Perfect. All right. The next one, it says 1 mole. How many moles are in 67.2 liters of carbon dioxide? And this is a gas. Carbon dioxide is a gas. So in our first example, this one, we just had to use the masses that were on the periodic table. And again, these are fixed numbers. So if they're fixed numbers, we don't need to worry about number of sig figs. So we didn't really need to worry about the number of sig figs in this problem. So again, if you had more digits past the decimal, you might have more 3 or 4 digits past the decimal than compared to mine. So in this one, my conversion factor is 1 mole of any gas is equal to 22.4 liters. So always start with what's given to you in the problem, which is 67.2 liters. I multiply it by my conversion factor. This unit gets dragged down here. I look at my conversion factor, 22.4 liters. Okay, so liters divided by liters, that will cancel out, and I'm to 1 mole. So like I said, liters will cancel out liters. And then I do 67.2 times 1 divided by 22.4, and my answer comes out to be, is that 3? 22.4, yes, so 3. But 67.2 has 3 sig figs, so I need to do 3.00. So my answer has 3 sig figs, and that is moles. So 3 sig figs for my answer. All right, so here in our last practice problem, it says what mass of silver chloride would be obtained from 3.0 times 10 to the 25th molecules. So again, here is kind of one of those mistakes that I was talked about in the previous slide. So silver chloride is actually an ionic compound, so this should actually say formula units. Okay, so thinking back to, again, my little mole conversion chart, we had moles, remember, and then we had volume, and then we had mass, and then we had particles. Okay, and this will also be molecules down here. Remember we said if we're dealing with molecules or formula units, that will all be included in the particle part. Okay, so we were given mass. Okay, so we're going to, and we need, so here, looking at our pathway, we're given mass, and we need to get over here to formula units, but you have to go from, again, these should be double arrows. Oops, Mrs. Spiteri. Okay, so looking, so we got to go from mass to moles, and then moles to formula units. So again, always start with what's given to you in the problem. So 3.0 times 10 to the 25th formula units. So multiply it. So again, formula units needs to go down here. Formula units. So I look, again, I need to go from formula units to moles so I can get to moles to mass. So in 1 mole, there are 6.02 times 10 to the 23rd formula units. So I'm now here at the mole stage, and then now I know 1 mole of any substance is equal to the molar mass of that substance. So I know multiply here. Mole needs to go in the denominator. So 1 mole of any substance is equal to, and again, we could be very specific if we wanted to write out the actual compound. I look on the periodic table. I see silver is 107.87 plus chlorine, which is 35.45. Again, use the exact numbers you find on the periodic table. Do not round up, do not round down. 143.32 grams of silver chloride. So I'm going to go 3.0 times 10 to the 25th times 1 times 143.32. All of that divided by 6.02 times 10 to the 23rd. And our answer comes out to be 7,142.19. But looking back to my problem, my coefficient here only has 2 sig figs, so I need to round my answer to 2 sig figs. So you could say 7,100 grams, or you can convert that into scientific notation. You could say 7.1 times 10 eq. 10 to the 123 third grams of silver chloride. And that's that.